The equation above is an equation for a hyperbola. It should look very similar to your ellipse equations. However, the big difference is that there's a subtraction sign between the two fractions. So when it's addition, you have an ellipse. Subtraction means hyperbola. So now some of the differences with a hyperbola. First off, in hyperbolas, a is always going to be your first number. So in this case, a squared is going to equal 9, b squared equals 16. So it's no longer the bigger one, it is always whatever comes first. Since in subtraction order matters, you can't switch the order of these around. So right away we know a squared is 9, a is going to equal 3, b is going to equal 4. So now to tell if it's horizontal or vertical, just like you're similar to ellipses, whatever number is with a tells you horizontal or vertical. So it's always the first fraction. Again, a is not always the bigger one, so it's always the first fraction is going to tell you which you're dealing with. So in this case, since y is first, that tells us we're dealing with a vertical hyperbola. And visually that means our two parabola-looking shapes are going to be opening up and down. Next, the center is the same as it's been all along. The opposite of what's ever with x, which in this case is a 2. Be careful because x is second here. And then the opposite of whatever is with y. In this case would be a 1. And the last piece we need is our c value. And this, for this time, different than an ellipse, we just have our normal Pythagorean theorem to find c. So we know a squared plus b squared equals c squared. So 9 plus 16 equals c squared. 25 equals c squared, which means c is 5. The last new piece that we have in hyperbolas that we haven't had any shapes so far are asymptotes. These are just to help with the shape of the hyperbola. So to find your asymptotes, what you do is just going to be plus or minus, because we're going to go from the center of our hyperbola, which you'll see in a second, and it is always the number under y. So 3 over the square root of the number under x. So essentially when it's vertical, you do a over b, horizontal b over a. That can get a little confusing, so if you just think about it as the number under y over the number under x, I think it's rise over run, so y over x, it'll be a little easier to remember. So now just putting all of this together, first we graph our center, which was 2, 1, put that point there. This is vertical, so that means we're going to use a to count up and down. So up 1, 2, 3, that's going to be one vertex. Down 1, 2, 3 for the other vertex. Just like before, c gives us our distance to our focus. So from our center, we count up 5 for the one focus, down 5 for the other focus. And then lastly, for b, all we really use it for is to help with these asymptotes, because it's in the asymptote slope. So from the center, again, this helps with the shape of the hyperbola. We're going to count up 3 and over 4. 1, 2, 3, 4, because slope always works rise over run. And then we'll count down 3 over 1, 2, 3, 4. So there's one asymptote, essentially the positive line. And then we'll do the negative one. So up 3, left 4, down 3, right 4. Oops. Notice as you create your asymptote lines, you should essentially be able to see this little rectangle here. You do not have to draw this rectangle, but just so you can see that the vertices are on that rectangle, all of those slope points work together, so it just helps kind of see that box. So now the actual parabola goes through the vertex, opens up, it hugs the asymptotes but never crosses them, hence why we use them to give us shape. So in this case, it's a wider hyperbola. And there's your graph of your hyperbola.